Section 3.3, the quotient topology. We've seen so far in this chapter that if we are given a topological space or spaces, we can form smaller spaces with the subspace topology or larger spaces with the product topology. The quotient topology is going to give us another way to form smaller topological spaces. But unlike with the subspace topology, where we threw away points from our set X, with the quotient topology, we're going to identify points from X, or sort of glue them together to get new topological spaces. So we have a number of preliminaries here before we can try our first exercise. Definition 0.15, a relation R on a set X is a subset of the product X times X. In other words, it's a collection of ordered pairs of elements of X. So if the ordered pair XY is in the relation, then we write XRY and we say that X is related to Y. Now we're only going to be interested in equivalence relations. Definition 0.16, a relation on X is called an equivalence relation if the following properties hold for all elements A, B, and C in X. 1, reflexivity, 2, symmetry, and 3, transitivity. You've seen all these properties before, and you've encountered a number of equivalence relations in your studies. Equality, for example, congruence or similarity of geometric shapes, isomorphism of vector spaces or linear spaces. So that's the sort of thing we're going to be looking at. And then very closely related to equivalence relations are partitions. Definition 0.17. A partition of a set X is a collection of mutually disjoint subsets of X whose union is X. So basically we're taking a set X and we're breaking it up into a bunch of pieces which don't overlap and which cover the whole set X. Okay. So for example, if you look at this picture down here, I have a set X consisting of the 6 elements A, B, C, D, E, F. And my partition is breaking that set into 3 pieces. One piece consisting of A, B, C, one piece of D, and one piece of E and F. Now you can get a partition from an equivalence relation by looking at what are called the equivalence classes of the elements of a set X. And so if X is an X, the equivalence class of X under this relation is denoted by bracket X, and it's the set of all elements P and X which are equivalent to X. Okay. It's a set of everything equivalent to X. So for example, this subset of X right here is the equivalence class of B, assuming that A and C are both equivalent to B. Whereas D is only equivalent to itself in this picture, so it is its own equivalence class. And, well, this could be written as the equivalence class of E if E and F are equivalent. Okay. This could also be the equivalence class of A or C, and this could equally well be the equivalence class of F. All right, so if we have an equivalence relation, we get a partition, and vice versa. Definition 0.23, a function f from x to y is said to be onto or surjective if f of x equals y. In other words, if the image of your domain x covers up the entire target y. Okay. In other words, for every y in your target y, there is some x in the domain x such that f of x equals y. Good. Well, let's actually define the quotient topology using all this stuff. Definition 3.11, let X be a topological space and A a set. It is not necessarily a subset of X. And suppose we have a surjective map, a surjective function P from our topological space X to our new set A. We want to define a topology on A using the topology on X. Okay, well, define a subset U of A to be open if and only if its preimage, P inverse of U, in X is open in X. The resultant collection of open sets in A that we get this way is called the quotient topology induced by this function P, and the function P is called a quotient map. The topological space A is called a quotient space. Okay, so let me say that again. We have a topological space X. We're mapping it onto A, and we test whether a subset of A is open by looking at its preimage in X and seeing if that's open. So let's look at a simple example here. Suppose we have a surjective map P from the real numbers to the real numbers greater than or equal to 0, which is given by just taking the absolute value. And it's illustrated over here. Here's R greater than or equal to 0. This is certainly a surjective function. Let's look at a couple subsets of our A here, of our R greater than or equal to 0, and see if they're open, okay, in the quotient topology. Let's look first at the interval from 2 to 3, not including the endpoints. Call that U. Its preimage under P would be everything whose absolute value is between 2 and 3. And we get a couple intervals that way, right? The interval from -3 to -2, and the interval from 2 to 3. And so the preimage of U is the union of those two intervals, each of which is open. Therefore, P inverse of U is open in the standard topology on R. And by definition of the quotient topology, that means that this interval U is also open in the quotient space. Okay. Let's look at another one, V here. It may not be quite as obvious that this should be open, since I'm including the point 0 this time. But its preimage under P is just going to be everything between -1 and 1, not including either endpoint. And that's certainly open in R. Therefore, by definition of the quotient topology, this subset V is open in the quotient space R greater than or equal to 0. So that's how it works. Now you might wonder what this has to do with the partitions and equivalence relations I was speaking about up here. Well, basically, that's how we're going to define our quotient map P. Okay. So that's what this next example is about. Suppose we start out with some partition X star of a set X. And we can define a quotient map P from X to X star by just taking every point in X to the corresponding element of X star, containing it. Right? So we're going to map an element X to its equivalence class bracket X. And this P induces a quotient topology on the partition X star. Okay. So if you look with me back at this partition that I drew up here, the set X, again, consists of the 6 elements A, B, C, D, E, F. And X star consists of just 3 elements, these 3 subsets of the original set X. And we're going to map, for example, A to bracket A, to the equivalence class of A. We're going to map it to this set. We're going to map B to that same set, and C to that same set. We're going to map D to the set bracket D consisting just of itself, and we will map each of these 2 elements to the single subset consisting of both of them. Okay. So in that case, P would be a function from a 6-element set down to a 3-element set. Certainly surjective. Okay. And so basically, as you can read there, we are identifying sort of these points together into a single set, or identifying these 2 together into a single set to get a smaller set X star. That's basically what I've written right here. Okay, well now we can finally do our exercise, 3.29. Consider the equivalence relation on the plane R2 defined by 2 points in the plane are going to be equivalent if the sum of their coordinates is the same. Describe the quotient space that results from the partition of the plane into equivalence classes in this equivalence relation. All right, well, what do these equivalence classes look like? Basically, once you have a point x1, x2, its equivalence class is going to be all the other points in the plane w1, w2, such that w1 plus w2 equals whatever the sum of your original 2 coordinates were. And that's just going to be some line in the plane of slope -1 through that original point x1, x2. Okay. And you'll notice that every such line crosses the horizontal axis in exactly 1 point, in particular the point x1 plus x2, 0. And so you could represent that equivalence class either as the equivalence class of the original point or the equivalence class of this new point on the x-axis. Because anything equivalent to this point is going to be equivalent to that point too, and vice versa. So we're breaking up the plane into all these diagonal lines. Alright, so what have I said here so far? Okay, so we're going to call R2 star a set of all these equivalence classes, a set of all these lines that fill up the plane. And I already said that every point is equivalent to a unique point in the horizontal axis. So in fact, R2 star consists of distinct elements, equivalence class of x0, okay, for any x in R. R here is sort of the horizontal axis. Well, that's more or less what I mean. So this means that a subset of the set of equivalence classes is just a set of the form A star, consisting of equivalence classes of points x0 on the horizontal axis for all numbers x and A, where A is any subset of R. Okay. So basically, we're taking a bunch of real numbers in a subset A, and then we're looking at all the corresponding points on this horizontal axis, and then we're taking all of these diagonal lines through those particular points, and that gives us A star. Now, we're supposed to describe the quotient space, so we got to say when a subset A star of R2 star is open. We're going to show that A star is open in this quotient space if and only if set A that it comes from is open in the real numbers. Okay? So that this quotient space R2 star is essentially the same as the topological space R that we all know and love. Now this phrase essentially the same here in quotes. There's a technical word for that we're going to learn in a future chapter, and that word is homeomorphic. So basically it just means that open sets in one space are exactly correspond to the open sets in the other space. That's what we're going to show. Okay, so well, you might get confused a little bit with what these A and A star mean. So let's run through it in a simple example here. Suppose that my set A of real numbers is just -1 and -2. Okay. And that gives me these 2 points, -1, 0, and 2, 0 on the horizontal axis. Well, then A star is a set of equivalence classes of these 2 points on the x-axis. And each of those equivalence classes is a line, so A star is a 2-element set, and those 2 elements are this subset of R2 and this subset of R2. Okay. You can ignore this P inverse of A star for a moment. Okay, well, what is our quotient map P? The partition of R2 and equivalence classes yields a surjective map P from our original space, the plane, to the set of lines, the quotient space. And remember, P of a point in the plane is just supposed to be the equivalence class of that point. Right? It's supposed to be the line, the diagonal line through that point, which we could represent either by this or by this. Okay. Well, what does it mean for, remember, we want to know when is A star open in R2 star. Okay. All right, well, the subset A star, defined like this, of the quotient space R2 star is by definition open in R2 star if and only if its preimage under this quotient map P is open. Well, what is the preimage of a collection of these equivalence classes? Well, let's run through the definitions here. It's a set of all points in the plane which get mapped to some equivalence class in A star. Okay. In other words, a set of points in the plane such that the equivalence class of that point is one of these equivalence classes in A star. In other words, it's this point x1 plus x2 comma 0 is equivalent to x0 for some x in A. And, well, is equivalent if x1 plus x2 plus 0 equals x plus 0. In other words, if x1 plus x2 equals x, then x is an A, so that just means that x1 plus x2 has to be an A. Okay. So that is a complicated way of saying that the preimage of a collection of these diagonal lines is just going to be the set of all points contained in those lines. Okay? I mean, set of all points such that x1 plus x2 is in A. All right. So A star is open if and only if its preimage is open. Remember, we're trying to show that A star is open if and only if A is open. And so you string those two things together, and it suffices to show that the preimage of A star is open if and only if A is open. And the good thing about that is that now we're not dealing with any strange space of equivalence classes R2 star. Right? Now we're just dealing with the plane R2 and the line R. So now we can get our hands dirty with what this actually looks like. Okay, so it's an if and only if statement. It means we have to show two directions. Let's first of all suppose that P inverse of A star is open in R2 and prove that A is open in R. Alright, well I've represented A in this diagram by this interval here on the horizontal axis. And then remember, A star is just the set of all of these diagonal lines which go through points with x coordinate in A. And then P inverse of A star would be the, not the set of lines, but the set of all points on those lines. In other words, the union of all of those lines. Okay, so that's just this diagonal strip here for this particular depiction. And I'm assuming that's in R. I'm assuming that's open in R2. So to show that A is open in R, I have to take any element x in A, and I have to find a basis element which contains x and is contained in A. All right. Now, given that x in A, I can look at this point x comma 0 on the horizontal axis, and well, let's see. That point x comma 0 is certainly contained in P inverse of A star, right? And so, because P inverse of A star is open, I can find some basis element, interval from A to B times interval from C to D for the topology on R2. I'm taking open rectangles as my base elements here, which contains that point x0 and is contained in the diagonal strip P inverse of A star. Okay. So this open rectangle is drawn right here. It goes from A to B on the horizontal axis and C to D on the vertical axis. And it contains that point x0. Okay, well, what I'm going to do now is take this little piece of the horizontal axis, which is contained inside of that rectangle, right, which is just the interval from A to B times the singleton set of 0. All of those points have a y coordinate of 0. I claim that that's contained in P inverse of A star. Well, yeah, it's a subset of the open rectangle, which was itself contained in P inverse of A star, so that's certainly true. Therefore, well, what does it mean to be in P inverse of A star? It means that if you add up the coordinates, you always get something in A. If you add up the coordinates, first coordinate between A and B and the second coordinate of 0, you just get that first coordinate. Okay, so that means that whatever the first coordinate is, anything between A and B has to be contained in A. So we get that the interval from A to B is a subset of A, and, well, it contains x because the point x0 was in this rectangle. In particular, the first coordinate x is contained in the first factor here, A to B. So we're done. These open intervals form a basis for R, so we've shown that A is open in R. Now we have to do the other direction. You're going to assume that A is open in R and prove that P inverse of A star is open in R2. So I have a similar diagram here. A, I'm sort of representing on the horizontal axis again. Suppose it's open. Take any point x1, x2 in the diagonal strip P inverse of A star. Well, then by what we had earlier, that means that x1 plus x2 is an A. And so x1 plus x2 would be this number right here, sort of on that same diagonal line. That's an A, and since A is open, we can find some basis element, open interval from A to B, which contains that number x1 plus x2. Good. And moreover is contained in this open set A. All right, that's what it means for A to be open. Well, now I need to take that open interval from A to B and somehow get an open subset of R2, which contains this point x1, x2, and is contained in P inverse of A star. Okay. And the idea is just to build all the diagonal lines that pass through those points between A and B, and then take the union of them, and I'll get this thinner horizontal or diagonal strip here, which is certainly contained in P inverse of A star. Okay. Let's try and write that out. Okay, we have AB, which contains x1 plus x2 and is contained in A. Then this point x1, x2 is in this set because x1 plus x2 is in AB, as we just assumed. And then this set is a subset of P inverse of A star because, well, what was P inverse of A star? The coordinates have to add up to something in A. Okay? But here they add up to something between A and B, and the interval from A to B is contained in A. So this is sort of the special case of W1 plus W2 contained in A. Good. So I found a set which is a subset of the diagonal strip P inverse of A star. It contains this point x1, x2. All I have to show is that this set is an open subset of the plane. Okay. But that's not so bad once you just rewrite it, right? Since this is equal to, what does it mean for W1 plus W2 to be between A and B? It means that on the one hand it has to be greater than A, on the other hand the sum has to be less than B. So if we just take the intersection of these two sets, we get this narrow diagonal strip here. Okay. But each of these sets is an open half-plane, and we've proven before that an open half-plane is an open subset of R2. And the intersection of two open sets is open. Therefore, this set is open, and put that together, you get that P inverse of A star is open in R2. And that completes our proof.